Good afternoon, everyone. I'm Lori DeToro, editor of Water Technology. Welcome to Top 5 Trends Driving the Use of UV Disinfection for Microbial Control, sponsored by Water Technology and Evoqua. Thanks so much for joining us today. I'd like to take care of a few housekeeping items before we begin. During this webinar, if you have any technical problems, please let us know by telling us in the question area provided. Also, if you have any questions for our speaker during the webinar, you can use the same area to ask those questions. We will get to as many questions as possible at the end of the live event. Questions that we do not answer will be posted on watertechonline.com as soon as possible. The presentation is also being recorded and will be available for on-demand viewing in the next few days. With the number of emerging microbial pathogens now displaying an increased tolerance to chlorine and pasteurization methods, this webinar discusses how to protect quality and brand integrity by using validated UV disinfection technology in product liquids, processed water, or industrial effluent. John McLean will leverage his more than 30 years of experience in the field of UV photolysis and disinfection during this presentation. He has an undergraduate degree in physics, an MBA, and has been engaged with UV companies since 1986. John is the VP of Research, Development, and Engineering within Evoqua's Aquatics and Disinfection Division and is an industry expert who speaks at conferences around the world. John, please get us started.
Thank you, Laurie. Thank you very much. Look, today we're going to focus on 5 of the top trends that we see in the food and the beverage markets. We're going to talk about UV, how it's made, where it's applied, and we'll look at some specific applications and some of the issues we see emerging. So as I said, we're going to cover some of the fundamentals of UV, the top 5 trends that we see persistently emerging across food companies, dairy businesses, and beverage companies. I'll give you some tips as to what to look for in lab design and equipment. So if you wouldn't mind, just complete this questionnaire for me. I'll wait a few minutes and then we'll look at the answers. Okay, so look, about 56% of the audience is currently using UV, which is great. It means that we have a quite knowledgeable base. We'll cover many of the applications that you have, and we'll introduce some new applications that will be able to solve problems for you or give you some fluids or some techniques that you probably hadn't considered. So we'll start with what's called the electromagnetic spectrum. This unifies all the different forms of radiation. It looks at the top shortwave radio, television, FM radio. It looks at radar, infrared light, the visible part of the spectrum. Infrared is called infrared because it sits above the red part of the visible spectrum. And we have ultraviolet light, X-rays, gamma rays, and cosmic rays. Ultraviolet is called UV because it sits next to the violet in the visible spectrum. So straight away, look, you can see that UV is invisible. You can't see UV with the naked eye. So not that you should ever look at a burning UV lamp, but what you see coming off is visible light, not the ultraviolet light. UV splits into 4 principal types: UVA, UVB, UVC, and the vacuum UV. UVA comes from black lights. It produces the white specks on a shirt in a nightclub. It's what the gecko breeders use. UVB is the sun tanning part of the spectrum. UVC is our world. That has profound germicidal properties. And then vacuum UV only exists in a vacuum. So as we move from the right to the left, we go from UVA through UVB through UVC through vacuum UV. And you'll see that as we move that way, the wavelengths become much more energetic. And there's a price to pay. As we move that way, they penetrate less. So we get better water penetration with the weaker wavelengths, which is intuitive. So if we start, this is quite a busy slide. If we take it one chunk at a time, in 1953, those two research scientists, James Watson and Francis Crick, won the Nobel Prize for discovering the helical structure of DNA. So right next to that, their photograph is a strand of healthy DNA. You can see the four bases. You can see adenine, thymine, guanine, cysteine. Think of a ladder. Think of a ladder and then twist it. That's really what DNA is. The next picture to it shows the replication, the healthy DNA replicating. So two daughter cells are formed from one parent. Then 2 becomes 4, and then 4 becomes 8, and so on. That's healthy cell replication. When DNA absorbs UV light, the rungs of the ladder, those cross bonds, they vibrate so violently that they rupture. And then the fragments form bonds with their neighbors. So drop down to the bottom left now. This is a process that we call dimerization. It's a process of breaking bonds in the DNA, and it renders the organisms non-viable. Now, it's a very important note. UV doesn't kill the bugs. It renders them non-viable. So if any of you are using these ATP-type test kits, they might show up positive even though the bug is non-viable. That's quite an important consideration. This slide speaks to some of the other examples of resonance that we see in nature. We are using light. Light is a form of energy, and we input light into the DNA and cause the bonds to break. It's well known. If you put a wine glass in a lot of sound at a certain frequency, the glass can absorb the sound energy and vibrate and shatter. There are bridges in London, and there are signs at the top right that order troops to break step when they march across the bridge, because the input of energy from the troops marching in step can cause small vibrations to become big vibrations, and the bridge will fail. The bottom left shows an electrical transmission pylon, which failed in the wind. And the bottom right is a very famous example. If you YouTube Galloping Gertie, it shows the bridge over Tacoma Narrows. This bridge famously absorbed the wind, energy from the wind resonated, and the whole bridge failed. The vibrations grew greater and greater, and eventually the whole bridge ruptured. Well, think of the bridge as the cross bond in the DNA. We use light. We cause it to vibrate so violently it breaks. That's really how UV works. This next slide is quite a busy slide. The top left shows some of the wavelengths that we produce by exciting electrons to different orbitals around the nucleus of the mercury inside the lamp. The middle graph shows the different types of light. It shows the output from a low pressure lamp. It shows the output from a medium pressure lamp. It shows where the DNA most strongly absorbs the UV light. So the germicidal effectiveness is about 265 nanometers. The right picture shows the mercury atom with the protons and neutrons in the nucleus and the electrons orbiting. UV light is made by exciting these electrons to higher orbitals. When they drop back to lower levels, they produce UV. So that this is used by the lamp builders to produce the right wavelengths for us to produce our effects. So think of UV as having two principal effects. One is disinfection, and the other is photolysis. Now, disinfection is used very broadly. It's used to disinfect processed water or product water. It's used to disinfect whey, marinades, brines. It's used to disinfect water for transport. It's used to disinfect effluent for washdown. It's used to disinfect even teas these days. We see a lot of heat-tolerant organisms emerging in tea. We disinfect the tea using UV light. They're all applications of UV for disinfection. For photolysis, we're able to break down ozone, or we can remove total organic carbon from water, or we can remove chlorine or chloramines. So we can remove chemistry or chemicals from the water by using UV light if the system is sized properly and designed properly. So just take a moment, if you would, and consider these. You know, are your interests principally disinfection, or are you interested in using UV to remove ozone or TOC or to dechlorinate? Just take a moment and let's just see where the consensus is. Okay, so that's quite a typical spread. Most people see UV as a disinfecting technology, some ozone destruction, some TOC, and some chlorination and dechlorination. So we'll cover all of these in some depth as we go through this presentation. Okay, so as we promised at the start, the top trends that we see, and we'll explore each of these in some detail. And we see these persistently across food, dairy, bottled water companies, alcoholic beverage companies, and carbonated soft drinks businesses. There is a very real need to reduce chemicals and additives. There's a contradiction here. You want to have shelf life without pasteurization and without preservatives. So it puts a lot of emphasis on housekeeping and all the ingredients themselves being wholesome. There's a very real need to prevent contamination. There's a threat to human health with pathogens. There's a retail threat from spoilage, the visual property of the food looking spoiled and consumers not buying it. Thirdly, we see an emerging threat of organisms that can tolerate heat or can tolerate chemicals. If you think about going on vacation, you immunize yourself. You allow yourself to be injected with a low dose of a certain bug or a virus, then your body makes antibodies to fight it. Well, look, we've been adding low levels of chlorine to water for generations now, and so it's little surprise that there are now many chlorine-tolerant bugs. There are now heat-tolerant organisms. There are now biocide-tolerant organisms. So that's a very real threat to your world. We'll explore the use of UV as a pasteurizer, as an alternative to pasteurization. And we'll look at some of the pressure that you are under to reduce the water that's released from the factory. We see some zero discharge facilities emerging, but we see much more pressure to reuse water. So trend number one, reduction of chemicals and additive solution. One of the big attractions with UV is what it doesn't do. It doesn't alter the taste or the chemistry. It doesn't add anything to the water. The pH won't alter, the flavor, the odor, the color won't change. It won't introduce byproducts into the water. It won't add any chemistry to the water. So it's very attractive in that respect. Now there's a downside too. It also means there's no residual. You mustn't see UV as a replacement for good housekeeping. You have to clean in place all the pipe. You have to keep your housekeeping standards as high as they've ever been. But certainly it's used to reduce the chemical input into process or product water. Number two, prevention of contamination. We are faced with both a risk to human health from pathogenic organisms, and we're faced with spoilage organisms that won't kill people but affect shelf life. Many of the microbes are shown pictorially. We have pathogens like Cryptosporidium and Giardia. We have very real concern with Listeria. Listeria is now practically impossible to kill with chlorine. We see molds and yeasts which can cause spoilage in liquid form. We see yeasts which can cause fermentation in liquid form, all of which leads to reduced shelf life. So UV is used as a powerful tool to eliminate all of these spoilers, be they pathogens or be they simply spoilers. Tolerance. We see more and more tolerance with microbes to chemicals, to even quaternary biocides. We see many species now that are tolerant to chlorine. We see many species now that are tolerant to heat. So as the organisms evolve, they're able to mutate and they're able to find ways of either growing thicker outer skins or somehow resisting the chemical attack. we see profound tolerance now with cryptosporidium and giardia for chlorine and with listeria. And we see thermophiles, heat-tolerant organisms. Bacillus bacillus ACB is a classic heat-tolerant organism. The pasteurizers cause ACB to germinate and spoil teas and other drinks. Pasteurization has been a staple. You know, the dairy industry has thrived on pasteurization for several generations now. Pasteurization is slow. It's a batch process. You have to stop the water, heat it to a certain temperature, hold it for a certain amount of time, and then cool it, and then use it. The big advantage with UV is it's not a batch process, it's a flow through. Now there are standards. The Pasteurized Milk Ordinance has adopted a number of standard requirements for UV, and we've listed some of them down below. UV systems have to be validated by a third party. They have to produce a dose of 120 millijoules per square centimeter. They need to have effective wiping systems. They need to be easy to dismantle for cleaning should the wipers not be sufficient. They need to have UV monitor cameras, and they need to have a very strong fail-safe protocol. If the system fails, it must fail safe. So there needs to be actuation of valves to dump the water. We cannot send improperly treated water forward. That's very important. And trend number 5 is really pressure to reuse. There's more and more corporate social responsibility with water users to capture their water footprint, to see how much water they use to make a volume of product. And water is used as a process for heating, for cooling. Pasta flumes use water to move pasta. Pea producers use water to move peas. There's a great deal of pressure now to reduce the amount of water and to reuse it. We see a lot of initiatives whereby grey water or effluent is put through UV properly and safely and in a very controlled fashion disinfected and then repurposed for rinse down or spray down. Drought is a very topical conversation here in the US. We see many areas which are drought prone, and these trends will only become more and more exacerbated as we go forward. And finally, cost. Water is still cheap, but it'll become very much more expensive. So more and more pressure to reuse. In terms of lamps, you'll hear 3 types of lamps discussed. The oldest style is what's called a low pressure lamp. This is akin to a fluorescent lamp that might be above your head in the garage. It's a very simple design, quite low germicidal output per unit length. And what goes into a lamp must come out. So in terms of the total output, we see about 30% coming off as useful UV, about 40% is visible light, and probably 30% is infrared. So the total is always 100%. Amalgam technology allows us to build higher powered low pressure lamps. Some of the biggest amalgam lamps these days go up to 1,000 watts. They have improved electrical efficiency, so we get up to 35% efficiency from these lamps. They make about 35% visible light, and they produce about 30% infrared. Medium pressure lamps have a strong advantage in that they are very small. The footprint is very small, so they can be packed into a very small area. Ships would tend to use medium pressure technology to disinfect ballast water because getting the equipment down to the bowels of the ship is very tough. You can't have a high footprint. The price they pay is electrical efficiency. They aren't very efficient. A medium pressure lamp is typically only about 10% efficient, 20% visible light and lots of heat. So there's a price to pay. You either have a very efficient but high footprint technology called an amalgam system, or you have a lower electrical efficiency but very small footprint medium pressure system. Wiping is critical. The wiper is a seminal and critical part of a UV system. The water will foul. If you're using a pasta flume or if you're using water to move carrots or peas or potatoes, if you're using brines, part of the preparation of cured meats involves lots of very cold, deeply chilled brines. these will all deposit foulant on the surface of the quartz. So we use a device a bit like a windshield wiper on a car. We have a wiper which is driven by a motor, constantly tracking backwards and forwards. You don't want your operators to have to dismantle the equipment all the time. It should be done automatically for you. So we can see the effectiveness of the wipe with the monitor cameras telling us that all's good. So this is a method of keeping the whole system free from fouling and working even though we're dealing with highly impaired fluids. Validation is critical too. The drinking water industry has led the world in the use of validation. It keeps manufacturers honest. It means that if a manufacturer makes a certain claim, they have to be able to verify through a validation document that they can actually deliver performance to meet that claim. Remember, we're dealing in light. It's very hard for you to know how much light has been put into the water other than having a validated UV system with a validation document. So insist that your UV providers are providing you with independently third-party validated machines. That means that the machines have been tested by a third party and they've been shown to do what the manufacturer claims they'll do. Validation process is complex, it's difficult to get through, very rigorous, but well worth it at the other side. You know, it weeds out the wheat from the chaff. So look, what to do next? We have a number of specialists that are available. I will be happy to take questions now, as Laurie indicated. David McCarthy is a veteran of the UV business. He's been in the industry for over 30 years, and he has a deep understanding of the application of UV for industrial process, for municipal applications. So his email address is shown on this slide. In here, I will be happy to take questions. I'll take them now, and Dave will be happy to take them when the webinar's over. These are my details. My name is John McLean. Thank you all for your time, and be welcome to, as Laurie said, be welcome to ask any questions. Thank you, Laurie.
Thanks, John, for a great presentation. Again, it's Laurie again with Water Technology, and we're entering the time for questions and answers from our listeners and answers from our presenter. If you have additional questions while we are having this part of the discussion, please type them into the question box and we will get to them as time allows. The first question we have is UV LED technology has made its way to the market. Do you see this as a replacement product?
Okay, that's a great question, Laurie. That's a very insightful question. Look, if we go back to what's out there now, look at the existing lamp technology. The oldest lamps are 30% efficient. Some of the modern amalgam lamps are over 40% efficient. Now, the modern amalgam lamps are up to 1,000 watts in output. The most powerful LED used for UV is only about 5 watts, and these lamps are only about 1 to 1.5% efficient. So they currently are only really suited for very, very small flows. There isn't the volume, there isn't the drivers aren't there yet to allow investment to make the leap for UV LEDs into disinfection, other than for minuscule flows. So we monitor them. Our feeling is that they're limited to very small applications for the time being. I think that they are some way off from entering the mainstream 6-inch, 8-inch, 14-inch pipe worth of flows. That was a good question, Laurie.
Great, thank you so much for that answer. The next one we have is, how does UV penetrate liquid sugar or brines to disinfect?
Okay, well, we would use a different geometry reactor. For some of the brines, you can treat up to a 70 Brix brine, a high invert sugar brine, a high invert Brix, very concentrated sugar syrup solution, which can be quite viscous. So we'd use a thin film device to disinfect some of the stronger, the higher Brix sugar syrups. For brines, we'd simply use lots of lamps with small path lengths. We will measure the transmittance of the fluid. We'll look to see how well the fluids transmit UV light. and we'll then design a system. We have a range of machines suitable for good water, a range of machines for sugar syrup, a range of machines for very low transmission fluid. And we have these deployed in the field now, so we can provide lots of good case study material to show people how they work, and we'll be happy to advise them as to some of the pitfalls to avoid.
Great, thank you. Next question is, what are the energy efficiency opportunities in wastewater treatment processes with UV technology, and is it cost effective?
Well, okay, these are some very insightful questions, first of all. I think the energy efficiency opportunities really surround how the fluid is handled. The oldest technique is to drop racks of lamps in an open channel. That's how UV started out in North America. These open channel systems suffer from very poor hydraulics. Everything else is in a pipe. So we would only build in-pipe systems. All of our wastewater systems are in pipe. So I think put it in a pipe, that's the place to start. Don't have poor hydraulics. Think about how the hydraulics are handled, and ask the UV provider to account for all of that. I think lamp technology will continue to be refined. I think that the lamp spacing is governed by the use of advanced CFD modeling. Computational fluid dynamics really is a very powerful tool to help us where to place lamps, how many lamps we need. You'll notice many of our designs don't have symmetric arrangements of lamps. The arrangements are asymmetric because we put the lamps where the water goes. The water isn't moving symmetrically through the structure, so the lamp shouldn't be symmetrically placed. So we have a variety of emulation tools. We have a lot of validated machines, so we know it's our job as manufacturers to be intimate with how these machines perform. And when we're asked to make performance guarantees, then we can, because we understand how they perform. That was another good question, Lori.
Thanks, John. This next one is extremely technical. I'm going to read it exactly as written, and if you need more information, hopefully the person who asked the question will let us know. Can I use a UV-rated 185 nm, which I'm assuming is nanometers, but I'm not 100% sure, for TOC destruct? Okay, good. For TOC destruct to also be effective for bacterial control, or do I have to have a 185 nanometer for TOC destruct use and a separate 254 nanometer UV for bacterial control? This is on an RODI water loop.
Yeah, okay. Well, look, using low pressure lamps are built to be rich in 185 nanometer light. They also produce lots of 254. So to answer to the question directly, no, you don't need a second UV system. If you've got a 185 nanometer system, then it will also produce plenty of germicidal UV. So both types come off one lamp. You might need different UV systems across different parts of the process. Using UV to remove TOC involves ion exchanges. It can involve carbon, so there could be other points to introduce bugs into that kind of loop. But to answer the question directly, no. If it's a 185 lamp, it also makes 254, so that will also be germicidal.
Thank you again. Next question is, are you working with any utilities offering energy efficiency incentives to implement UV technology? And what are the popular applications from a standpoint of energy efficiency?
Well, we are working with a number of utilities, a number of municipalities to replace older UV systems that are energy inefficient. Some of the older open channel systems are very power consumptive, so we've replaced some of those with some more energy efficient systems. We do partner with a wide variety of sensible, reputable partners. If people on the call have ideas, I'd welcome them to email me directly afterwards. If it's a sensible collaboration, we'd be very glad to consider it.
All right, the next question. How does UV treat wastewater to meet environmental regulations for release?
Well, if we add chlorine to wastewater, we risk elevating a compound called a trihalomethane, which is a byproduct chlorination, which is implicitly a carcinogen. It can do damage and harm. If we then try and discharge chlorinated wastewater, we have to remove the chlorine. Otherwise, we can have a devastating effect on the natural flora and fauna in the lakes and the rivers. So UV has long been very successfully applied to wastewaters. We have a very wide variety of applications, from pristine RO permeate, really high quality wastewater destined for direct potable reclaim. We have lots of stream or ditch discharge applications where the UV is in a pipe disinfecting 6, 8, 10, 12 or even 22 million gallons per day of oxidation ditch or primary and secondary treated effluent. We have a number of combined sewer overflow installations where we are disinfecting the storm surge from a high rain event. It needs to be properly sized. It needs to have enough lamps. It needs to have effective wipers. That's very important. We put an access hatch on the wastewater machines so as operators can get their hands into the reactors and needs be to remove algae or debris that could stuff off a clarifier. It's very hard. You can't take an ultra pure water machine and expect it to work in wastewater. You have to design it properly. It's a different geometry, different type of lamp, more lamps. But if you understand that, it's a very successful application. And we have many excellent case study quality and reference grade installations.
Great, thank you. The next question is, would multiple lamps be required for chlorine removal and disinfection on the same stream?
Yes, you need to have a much higher UV dose to remove chlorine. I was at a pilot in Tucson on Wednesday of this week, and we took the free chlorine down from 5.4 to 0.2 milligrams per liter in a single pass. So any machine designed for dechlorination will also give you a very high disinfecting dose. So you do not need a second UV system for disinfection. If you're dechlorinating, then you will get a very high disinfection dose. Removing chlorine is involved. It's difficult to get right. It's a function of pH, the water chemistry, what else is in the water. There are lots of scavengers. Bicarbonates will scavenge the photons that can remove the chlorine. So it's a thing we have to consider very carefully. When it's sized right, we'll ask lots of questions, and then when we have the answers, we can make a proposal, and then we'll make a guarantee for the effluent level of the chlorine. We'll give the operator, we'll tell you if we can reduce it down to 0.2 or 0.1, provided the input is no higher than this. So we'll be able to have quite a very strong process understanding of the application.
The next question is, with regard to the types of lamps, low, amalgam, and medium pressure, do they each have an optimal wavelength range?
Yes, they do. If you go back to that slide, lamp technology, the low pressure lamp and the amalgam lamp are what are called monochromatic lamps. They only produce either 185 or 254 or a bit of both. Medium pressure lamps are what we call polychromatic. They produce a broad spectral output. If we go back to study the germicidal efficiency, if we go back to an earlier slide in the presentation, I'm just going to find it now. We can see, so if we go back to this slide, we can see in the middle, so we can see the low pressure UV lamp is one single output at 254. The medium pressure output is much greater. We've exaggerated the scale. Had we drawn these to scale, the low pressure output would be a small dot. The germicidal effectiveness has a peak at 265 nanometers. What we want is UV around the 265 nanometer mark. That's where it does the most damage to the DNA. So yes, each lamp has its own spectral characteristics. We build lamps from synthetic quartz for the deep UV for TSC removal, and we build lamps from regular quartz for regular disinfection and for use in pools and recreational water.
Thanks again. We are getting a lot of questions, so we will end at one, but one central. But the next question I have is, do you have an AOP process?
We do. We see AOP is a very critical part now of a modern wastewater plant. Look, if we study some of the compounds of emerging concern or some of the new problems we face in wastewater plants weren't built to take out vitamins or hormones. They weren't built to take out synthetic organics. They weren't built to take out perfluorinated compounds. They weren't built to take out insecticide or herbicide. So all these problems now are emerging. So we have an AOP system. We use an electrode inside the reactor. Many people use hydrogen peroxide in UV, but peroxide has a fundamental flaw because it doesn't absorb UV very well. So that the conventional AOP systems are very inefficient. Most of the peroxide goes straight through the UV system. We've developed and optimized an electrode, so we generate the active species in situ, and then we stuff them off the electrode onto the UV lamps. So we have a non-chemical AOP. We pilot this, and it works very well. So yes, we have an AOP process, and we see it as a critical part of our product portfolio.
Right, the next question I have is, what are your thoughts on using UV to dechlorinate ahead of reverse osmosis?
I think it's the right application. I think many membranes these days are very intolerant of chlorine, so you have to be very careful exposing a cellulose acetate membrane or the different membrane material to chlorine. So again, it has to be sized properly. You have to ask a lot of questions. You have to understand the pH of the water. You have to understand, are there chloramines present? Lots of questions to ask. But when you ask the right questions, funnily enough, it produces the right answers, and you can size it properly. So long as you understand what you're doing, it's a good application. You can't take an ordinary UV system and expect it to be an effective dechlorinating agent. You need to properly size it for that specific application. But a very high dose, the machines are bigger than disinfection machines. They look slightly different, but again, when properly sized, yes, it's a good application.
Okay, the next one we have is, we store millions of gallons of water with 2 to 25% glycols in above ground metal tanks or underground tanks. Fluid is collected in different ways, trucked, pumped, piped into a tank, small quantities every day. What would be the best way to treat with UV, and what type of costs would there be?
Well, certainly, it's perfectly treatable with UV. Depends how much glycol's in there. It depends what the challenge is. If you're trying to remove the glycol, or if you're trying to disinfect, we'd answer it differently. It certainly is very doable. We have a number of other customers who have similar compounds in water, and we successfully treat those. So what I would urge the person who asked that question to get hold of Dave McCarthy or me, and then we'll answer that directly offline.
Great. Another specific question. Do you have any industrial applications of UV for amine or azoles destruction?
What was the first word you said? Was it amine?
Amine, yes.
Amine, okay, yeah. Look, we do a lot of monodiene trichloramine destruction. We look at the way that these molecules absorb UV. We look at what wavelengths they can be broken down by. We study the molecule. We look at what chemical bonds they have, and then we look where these bonds will resonate. Like we showed all the examples of all the resonance. So we look at how the bonds absorb the UV. We will then size a system to remove it. If it's something we haven't done before, then we will gladly pilot. We have skid-based systems and container-based systems that we can deploy on a pilot basis, and we can then verify we get the performance we expect. So we have a lot of experience of monodiene trichloramine and other compounds. Depending if the compound is large, high molecular mass, they're generally pretty easy to break down with UV. The smaller ones are the harder ones because they are more tightly bound. So it's on a case-by-case basis. Yes, it can be done. If we haven't already done it, then we'd be happy to do a pilot.
Great. Next one. I have heard that some pathogens can repair the UV damage to their RNA and DNA. Is this a realistic concern?
Well, it's certainly correct. There are some pathogens which have always been able to repair themselves. There are two repair mechanisms. One is a light repair mechanism, one is a dark repair mechanism. They only occur if a very low dose of low pressure light, monochromatic light, is used. If the amount of damage that gets done to the DNA isn't sufficient, then the bug can repair itself. So typically you'd have an old low pressure system without proper wipers, and you then put the water in a pond or a tank exposed to sunlight. The water hasn't received a high enough dose of UV because there were no wipers or the system wasn't being wiped. And then it's stored in sunlight because sunlight can trigger these processes. So the answer is very direct and very simple. Put it in a pipe, use medium pressure equipment, make sure you've got effective wipers, and keep it dark. And then repair doesn't occur.
Next question involves reverse osmosis again. Have UV systems been used effectively as a pretreatment step in front of reverse osmosis systems to economically prevent, reduce, and control biological fouling of the RO membranes?
They have, yes, they have. It's a pretty well studied case. You know, it's a well documented case. We have lots of examples of exactly that. We have to be careful where we position the UV. If the water is high quality to start with, we can get hydroxyl radicals coming off the UV system, which can actually damage the membranes. We've got to position the UV far enough away from the membranes to cause no damage. But yes, it can be done. Again, if the questioner wants to approach me or Dave McCarthy offline, you know, we'll give them some cases as to where that's been done, what to look for, and you will see. You know, I would say that we're working in collaboration with some very effective filters. You know, we use the Vortisand filter a great deal before the UV and particularly before membranes. So filtration is a critical part of making the UV performance optimized and indeed optimizing the membrane performance. So I'd look to a high process performing filter like a Vortisand, or even a VAF screen before the Vortisand to make sure that the water has been properly prepared for UV and then properly prepared for the RO membrane.
All right. I think you touched on this topic a few minutes ago with another question, but is medium pressure more effective than low pressure for chlorine and chloramine destruction?
It is. If we look at how, you know, chlorine goes in solution depending on the pH in different forms. So we look at each form, they do absorb UV more generally. So medium pressure tends to be a better way to dechlorinate. It certainly is a better way to dechloraminate. If there's chlorine, there's probably chloramines as well. So we would tend to lead with medium pressure for a dechlorination or dechloramination application, just because those chemicals, the chemistry absorbs UV more resonance occurs, more bonds get broken. So it's more likely to work if it's a medium pressure system than if it's a low pressure system. So yes, we would prefer medium pressure for those photolysis type applications.
A little bit related, does it make sense to use medium pressure lamps for flow streams that have a low conductance value?
Well, you know, conductivity isn't so critical to us. What else is in the water, which will impair the passage of light, is more important. If the conductivity isn't very high, it probably means there are other things in the water which are going to, you know, connect. There could be solids, particle. The distribution of particle size is very important. Color is very important. I would say that aside from needing to know the flow rate, the UV transmittance is a critical measurement to take. So I would focus more on transmittance than conductivity. We do a lot of work with brines. We do a lot of work with injection waters for platforms, a lot of UV on ferries, on vessels for ballast water disinfection. Lots of water is forced down hole for the oil companies. Lots of fracking now uses very high total dissolved solid, high TDS, very concentrated brines. So I would say the transmission is the transmittance of the water is a critical factor. The path length between the lamps is therefore very important. We can't have one powerful lamp in a big fat chamber. You're better off having 6 or 7 lower powered lamps in a chamber, so we aren't trying to cast the UV too far. So the optical transmittance is more important than the conductivity.
Great, thank you. We have a few more questions left. What is the typical life of a lamp, and what can affect the lamp's life?
Well, what affects it is starting and stopping. If you want to have perfect lamp life, then never turn it on. People will turn them on. So what I say is, if you must turn it on, don't ever turn it off. If you can leave the lamp on, from a low pressure lamp, you'll probably get 2 years. You might even get 20,000 hours of life from a low pressure lamp. From a medium pressure lamp, you tend to get about 8,000 hours. So I would limit lamp life to 15,000 hours for a low pressure lamp. I'd limit it to 8,000 hours for a medium pressure lamp. Try and avoid a very aggressive start and stop cycle, because that will shorten lamp life. Try and reduce the number of starts and the number of stops per day. Up to 8 start-stops a day is fine. That lamps can cope well with that. But avoid starting and stopping them 6 or 7 times an hour, because that certainly will shorten lamp life.
Great, thank you. Next question is, what type of pretreatment do you prefer to see for drinking water from surface supplies?
That was a good question, Laurie. Hello? Hello?
Hi, I asked a question. Maybe it wasn't heard. I'm sorry. What type of pretreatment do you prefer? Can you hear me now?
Yes, I can. Yeah.
Okay, good. What type of pretreatment do you prefer to see for drinking water from surface supplies?
Well, we need to have some form of filtration. We see a lot of water sand filters being used very successfully in front of the UV equipment. The water sand uses a macro sand. So honestly, the more the better. It's well worth people investing in filtration to optimize the UV performance. The more you can raise the transmittance, the lower the power you'll need to use. So spend the money pre-treating the fluid generally. Surface waters are generally poorer than groundwaters because of the aquifer that they're percolating through. So we see lots of sand, we see lots of multimedia, we see flocculation, DAF, we see coagulation, the usual physical and chemical treatments before the UV. But it's a it's a critical area to really get to optimize the performance of the UV system.
Okay. Next question is: I've heard that UV systems validated in Europe require more energy and underperform because they are required to use ozone-free quartz. Is this true?
It is. Yes, the Germans have a certain standard called the DVGW. The Austrians have an O-norm standard, and they are indeed required to put additives into the quartz. They have a very specific dose. They validate around a dose of 40 millijoules. Here in the US, we have different doses. We have to verify the dose algorithm rather than validate to a certain number. So it gives us much more flexibility in application. Yes, it's true that the European validation protocols are more energy consumptive because there's more to impede the passage of light from the lamp through the quartz into the water.
All right, our next question. Microorganisms have been known to develop tolerances to pharmaceuticals. Do they also develop resistance to UV?
Well, look again. These are some really good questions, Laurie. No, they don't. And remember how we work. UV is absorbed by the DNA, and we blow apart the DNA. The DNA is the critical part of enabling a trait. You know, because of your DNA, your hair is straight, or your eyes are blue, or you're tall, or you're short. So we blow apart the DNA. So organisms cannot develop any tolerance to UV. They cannot develop any ability to resist UV because of how we work. So UV has been successfully applied since the late 60s, early 1970s. It's very exhaustively researched and scrutinized, and no research groups have found any evidence of any tolerance to UV. The repair mechanisms are documented, but they are limited to low pressure light in sunlight and linked to very low doses. So really the trick is use a validated UV system. A dose delivered to all the water is known to be a certain number. And that takes away all the guesswork.
Thanks. The next question, are there any applications that are considered ideal or in which UV is more commonly used versus other technologies?
I think it's the standard now for RO permeate. I think it's the standard now it's becoming the standard in dairies to replace pasteurizers. It's a very common barrier now for drinking water because of the chlorine tolerance. Ships, vessels use ballast water to use UV to disinfect ballast water, although UV is losing favor in ballast water in favor of some of the electrochlorination techniques. I think the microelectronics industry make very, very high quality water. They use lots of UV for TOC destruction, for disinfection. UV works very well to deozonate water, and it works very well for some of the more bizarre fluids like the brines, the marinades. As we start to see these heat-tolerant bugs propagating and proliferating, then more and more UV will be used by the tea manufacturers and the non-alcoholic carbonate or carbonated soft drinks companies who want to extend shelf life and keep their products safe.
Thank you again very much. This concludes our presentation today. We will post responses to the questions received during the webinar on our WaterWise blog at watertechonline.com. All attendees will also receive an email afterward with a video link to the presentation, and you'll find a link to a brief questionnaire. Please take a moment to complete it and let us know how we performed today during this event. We appreciate you taking the time to join us, and thanks to presenter John McLean and our sponsor Evoqua for today's presentation.